Welcome back to Chemistry Exams Prep. This is Dr. Kulbhushan. This question is asked by Miss Shirin from the Department of Chemistry, An-Naza University, Palestine. This question is asking about the order of acidities of these following four compounds. Compound A is a simple alcohol. Compound B is phenol. Compound C is a substituted phenol, para-chlorophenol. Compound D is also a substituted phenol, para-nitrophenol. So before we start to answer and draw some structures, first of all we need to review the definitions of Bronsted-Lowry acid bases. So Bronsted acids are the species that can give protons, and Bronsted bases are the species that can accept protons. So here structure A, it's a simple alcohol. So, and alcohols are less acidic than phenols because the phenol's conjugate base, phenoxide ion, is resonance stabilized. However, the alcohol's conjugate base, the alkoxide ion, is not resonance stabilized, and the more stable the conjugate base, higher the acidity. Now let's quickly draw out the conjugate bases of all of these four compounds. So conjugate base is the species that is formed after the removal of the proton from an acid. So once the proton is removed, you form the alkoxide ion in cases of alcohols. Now this alkoxide ion, the negative charge on the oxygen is localized. There is no resonance stabilization of the charge. Therefore it is less stable conjugate base, and that's the reason that alcohols are less acidic than phenols. Now let's draw the conjugate base of phenol. So the phenoxide ion can undergo resonance. So let's draw the resonating structures for the phenoxide ion. Once the pi bond of oxygen reforms, then the negative charge is now on number 2 carbon, means ortho position. In next resonating form, the charge is at para position, and in another resonance form, the charge moves to the carbon number 5. Now we can draw the resonance hybrid of this conjugate base, where the oxygen gets a partial negative charge and there is a partial double bond in all of the carbons on the benzene. The ortho and para positions are now partial negative. So we can see now how the negative charge has been delocalized over the entirety of the molecule. And this resonance delocalization of the negative charge is what stabilizes the conjugate base phenoxide ion, and that's the reason that phenols are more acidic than regular alcohols. So we know now that out of A and B, B is more acidic than A. Now let's see the effect of acidity when an electron withdrawing group is present. For example, here the chlorine has very high electronegativity, so it tries to get the electrons through the sigma bonds, and this kind of delocalization of electrons via sigma bonds is a permanent effect. It's known as inductive effect. Inductive effect is a permanent effect, and once you have electron withdrawing group present, it stabilizes the conjugate base further. So if you draw out the conjugate base of the parachlorophenol, you may see quickly how this is even more stable conjugate base than the phenoxide ion because of the high electronegativity of chlorine. Chlorine also gives the electrons to the ring, but that is through resonance, and it takes electrons, means all the halogen atoms, they will take the electrons by their inductive effect, and their inductive effect is in fact stronger than their resonance effect or mesomeric effect. So that's the reason that parachlorophenol is more acidic than the phenol. So now let's draw out the conjugate base and resonating structures of paranitrophenol. So once the proton is off, then you get your oxygen with the negative charge, and let's draw the nitro group in a more suggestive fashion, which shows the charges on oxygens and the nitrogen. So now you can draw the resonating structures. You will notice that the first structure is similar to what we have seen in case of phenol. However, once you move the negative charge and form another resonating structure, now the charge can be delocalized over nitro group. As you see now, this is the special resonating structure where the negative charge is on oxygen, not on the carbon, just like in case of phenol or parachlorophenol. And since oxygen is more electronegative, so it likes to hold to the negative charge better, and that's the reason that this is one of the most important resonating structure of paranitrophenol. You can draw out the other structures the same way as we did in case of phenoxide ion, and let's just draw the resonance hybrid now. So we can quickly see here partial positive charge on nitrogen and partial negative charge on the either oxygens. Again, the ortho positions are partial negative charge, and so this is the resonance hybrid. can see quickly why the paranitrophenol will be even more acidic than parachlorophenol and phenol, because this time the phenoxide ion is even better stabilized by a very strong electron withdrawing group, nitro group. So now just to recap this, the alcohols are not very acidic because their corresponding conjugate base is less stable because they do not show the resonance. Phenols are more acidic than alcohols because the phenoxide ion is stabilized by resonance. And if you have a halogen atom on a benzene ring, it takes away electron density. Hence, parachlorophenol is even more acidic than phenol, and paranitrophenol is the most acidic among these all four compounds here. So if we see our choices, B seems to be the correct answer because D is more acidic than C, and C is more acidic than B, and B is more acidic than the A. Alright, so if you have any questions, please let me know. Thanks for watching.